working on variety of other things that can be done from cosmic microwave background, particularly on small scales, as I'll tell now. So this beautiful picture, so this is the actual South Pole telescope. So it's a 10-meter diameter telescope, so it's huge, and it's at the South Pole. Okay, so we'll also show some really pretty pictures from the South Pole. So besides doing science, the other nice thing about being at South Pole is we can take lots of amazing pictures. Okay, so I want to start with this slide with the motivation of why do we want to do cosmic microwave background science, and I want to start with the statement. Okay, so the standard model of cosmology, which is a Lambda Cold Dark Matter model, as you might all know, it has been extremely successful in describing the observations that we have made over now 2 to 3 decades. Okay, so that is great, and I will show you some plots of why that is actually true. However, there are so many things that we don't understand about this model. Okay, first thing is that this model has inflation in it. It has dark matter in it, dark energy in it, but we actually don't understand the properties of any of these things clearly. And then the other thing is that as data becomes more and more sensitive, we have different cosmological observables. Like, for example, there's cosmic microwave background. There could be baryonic acoustic oscillations. There could be supernova and so many other things. But the results that we get on cosmology from each of these probes, they don't agree with each other. Okay, so these are tensions that exist between probes. These tensions could be real, which signifies that we might miss some important physics in this model, or this could be some systematic in each of these datasets. So we want to make make these data even better to basically disentangle between these two things. And the third one is that so there could actually be deviations from this model. Okay, so for example, there could be more number of relativistic species, which is normally called the N-effective. There could be neutrinos, with masses. And then gravity could actually deviate a little bit from general relativity. So these, I think, are the main motivations of why we want to do these kinds of science. Okay, and then in this talk, I'll try to motivate that current and future cosmological surveys are exactly designed to answer these questions. Okay, so this is the overview. I think I'm going to skip the first part a little bit because you all heard from Rad earlier today about most of these things. So I'll go really fast. So I'll start with the introduction to standard model, and then get into cosmic microwave background, but mostly into the observables. Like what exactly are we observing with these telescopes? Then I'll tell you what is the state of the art in terms of data sets for these observations. And then I will focus on these two results. So the first one is called the kinematic Sunyaev-Zeldovich effect, and I'll tell you what that is, and how we can use that to probe the epoch of reionization. Okay, so what this epoch of reionization is the epoch when first stars and galaxies formed in our universe. So then I will tell you about the thermal Sunyaev-Zeldovich effect and some astrophysical observables for that. And finally, if I have time, I'll get into some cross correlations between CMB observables and other galaxy surveys, like for example what Dominic was interested in. Okay, so I'm going to skip these things really fast. So you saw a different version of this picture today, but I like this version because it kind of emphasizes the different research that I've been doing over the years. So first there was inflation, followed by the period of hot Big Bang. Okay, so you might all know that detecting the primordial gravitational waves is the smoking gun for inflation, and we've been spending so much time and energy on doing this particular thing. Okay, so then for 400,000 years, universe was just extremely hot, and as a result, it was ionized. So there was just free electrons, so no neutral atoms. And as a result, light cannot travel in a straight line. So light, the mean free path of a photon is extremely small. So it tries to travel in a straight line. It gets hit by an electron, free electron, changes direction, gets hit by another free electron, changes direction, and this happens for a long period of time. Very similar to what happens inside our sun. But over time, the universe is expanding and cooling down. And around 400,000 years is when the universe is cold enough, around 3000 Kelvin, when neutral atoms, basically hydrogen, started to form. So now after hydrogen is formed, the universe is very transparent. So the photons can travel towards us without any interruption. Okay, so the farthest that we see will be the cosmic microwave background. And then over so many millions of years, nothing really happened in the universe. It's called the dark ages. It's very boring. It's just neutral hydrogen. Okay, but over time, neutral hydrogen will start to collapse under gravity. Okay, so then halos form, and that's when first stars and galaxies are forming. Okay, right. So that's this simple. So when first stars and galaxies are forming, that's reionization. So when first stars and galaxies are forming, so they emit very, very strong ultraviolet light. So what this ultraviolet light does is that it keeps an electron from the hydrogen atom, and universe start to go through this epoch called reionization. Okay, so now we have free electrons again. So these free electrons become more observable in the CMB polarization. Okay. So then later, all the other structures form. We have galaxies, galaxy clusters, the cosmic web that we observe with all the different galaxy surveys we see. Okay, so putting this all together, so the origin is inflation plus a hot Big Bang model, followed by the gravity determined by general relativity. That shows grow via hierarchical clustering. And then the matter, so it's mostly filled with dark matter and dark energy with roughly 5% the normal baryonic. Okay. So the question is, how did we actually get this? And that's where cosmic microwave background plays a really key role. Okay, like how did we get to this? So the classical pillars of Big Bang cosmology is built on these things. Okay, so first is that the galaxies, so the expansion of the universe. So this is recession of galaxies. Okay, so this is like the Hubble. And we also have the production of light elements in the very early universe called the Big Bang nucleosynthesis. Okay? Because, for example, these light elements cannot be produced by stars that we have. So now we are currently in this era of extremely big data, and now we have so many other observables which fine-tunes this model. Okay, so we have gravitational lensing, we have clustering of galaxies, we have velocity reconstruction, we have galaxy cluster abundance, and so many other things. Okay. So that's when we get into the cosmic microwave background. So this is the remnant radiation from the Big Bang, predicted by Alpha Ehrman and Gamow in 1940s, and then 20 years later, accidentally discovered by Penzias and Wilson. So this is really like one of the compelling evidences that Big Bang, really happened in our universe, because this is really the light from the Big Bang, and the light is partially polarized. So that's because around the time of recombination, which is the surface of last scattering, there are still some free electrons. And when free electrons interact with CMB photons, they induce polarization. This is linear polarization. I won't get into too much details about that. And the other important property of cosmic microwave background is that it's very homogeneous, meaning any direction you look, the statistics of this radiation is very, very similar in any direction. There are extremely small fluctuations around the mean temperature of the universe, which is roughly 2.7 Kelvin. And these fluctuations are 1 in 100,000. That's the level of fluctuations. And when we discover these fluctuations, when we observe these fluctuations, we can do a lot of science. Okay. And then, the way when we think about this, the whole cosmological model, or the timeline of the universe, we shouldn't be thinking about this in this 2D space. It's better to think of in this as a spherical shell, because we are at the center, and then the farthest that we look is a cosmic microwave background. So this region is opaque. That's the first 400,000 years. Then later, all the structures form and everything, right? So cosmic microwave background is basically free streaming towards us, and it interacts with everything that we know in the universe. As a result, you can do a lot more with CMB. Okay, so CMB is, it's great to study the primordial universe, but since CMB is interacting with everything that we know in the universe, CMB basically acts as a backlight. Okay, so all the structures we see, all the galaxies we see, they all interacted with CMB photons. Okay. So that interaction, it's extremely small. It's only like 10% of the CMB photons interact with these things. So they give rise to this additional anisotropies in the cosmic microwave background, and these are called secondary anisotropies of the CMB. Okay. So as a result, besides learning about the origin, CMB serves as a backlight to study star formation, to study the contents and evolution of the universe, which I will tell you how. And when I talk about these secondary anisotropies, mainly I will concentrate on these three things, because these are the most dominant effects. The first is gravitational lensing. So it's basically CMB photons are traveling towards us, and when there is matter in the universe, in the foreground, the path of the light is going to bend. And the amount of bending, the deflection angle, it's proportional to the mass in the particular location of the universe. So when we detect this, we actually learn about structure formation. Okay, we learn about how these structures form in the universe. So then what happens is that later time in the universe, these galaxies are forming, galaxy clusters are forming. And galaxy clusters and galaxies are normally hot. They are hotter than the average temperature of the universe. As a result, they have free electrons. Okay. So again, when there is free electrons, the CMB photons are going to interact with the free electrons. And this effect is called the inverse Compton scattering. So what it does, it actually induces extra energy into the CMB photon. So this is a really amazing effect, which you'll see in some pictures later. So what happens here is that if you look at that region of the sky with the CMB telescope, okay, observing in a given frequency band, okay, so the CMB photons are coming towards us, but in a particular location, if there is a halo and it has free electrons, the CMB photons in that location have now gained energy and moved to a different frequency band. As a result, when you're looking at that region, you see a decrement. Okay, so this is called the inverse Compton scattering, right? And you'll see in the pictures that this is actually a very nice way to detect galaxy clusters. So then what happens is that these halos in the universe, none of them are static. Everything in the universe is always moving. Okay, so this is motion. These are peculiar velocities with respect to the CMB rest frame. Okay, so CMB is moving with the Hubble flow, but then there are like peculiar velocities of galaxies, and if the halos are moving towards us, they induce a Doppler boosting. Okay, so they do a Doppler blue shift. So the photon of the CMB basically gets an increment. But if these halos are moving away from us, the photons get a decrement. So it's called the Doppler redshift. Okay, so these are the three main effects, and then there are like all the other things that we actually haven't detected, but there are so many other things that we can actually detect. So you can see this photon is actually moving with the world motion. Okay, so as a result, when you use gravitational lensing, you study structure formation. When you look at thermal Sunyaev-Zeldovich effect, you learn about hot electrons in the universe. When you learn about KZ, you learn about velocity deconstruction in the universe. Okay, so all these things are excellent probes of cosmology and structure formation. Okay, yeah. So basically, you can use CMB as a backlight. You can learn about so many things. You can learn about inflation. You can learn about reionization science. You can learn about structure formation, and you can learn about impact of baryons on structure formation and so many other things. Okay. Okay. So now, okay. So those are all the qualitative explanation of all of these effects. But what do we actually observe? Okay. So I'm not going to discuss too much about what the power spectrum is because I think you all know. But yeah, so that's we have the image of the sub-millimeter sky. We take that image. So this is from Planck. We basically take the Fourier transform of the image, two-dimensional Fourier transform if it's very small region, and then take a radial average of that. So basically, what you estimate here is the variance in that map as a function of angular scale. Okay, and the smaller the angle, the more the number of data points. The larger the angle, the less the number of data points, and then you get this plot. Okay, so the horizontal axis here is the inverse of the angular scale. So when you're looking at the left side, you look at really large regions of sky. When you look at the right side, you're looking at extremely small regions. Okay, so that's the angle between these two points. Okay. Okay. Then I want to show this plot. Okay, so this basically shows the state of the art of these power spectrum measurements. So what I'm showing here is that on the top, it's the temperature power spectrum of the CMB. Then we have the E mode power spectrum of the CMB. So then in the bottom, you have the cross correlation between the temperature and the E modes, because all of these things are coming from the density perturbations in the early universe. So there is basically a correlation between the temperature and the E modes. It's not very strong. It's only like 20% level, but there is nevertheless a correlation. Okay. So these are mostly observations made by Planck, and on large scales you also have BICEP. Let's not worry too much about BICEP here. Okay, so then what we do is we basically take CAM software, and we basically treat the contents of the universe and get the best fit curve. Okay, so that's basically how we derive the Lambda Cold Dark Matter model using, for example, from Planck observations. Okay, but so this is great. But what's even amazing is this, right? So then what happens is that later all the other experiments are now starting, right? So we have experiments like South Pole Telescope, experiments like Atacama Cosmology Telescope. So all these things are also measuring the CMB. And amazingly, all the data points are lying like bang on the theory curve that Planck predicts. Okay, so that's, and then this is basically like the recent measurements from the South Pole Telescope. So you can actually see how well these data points line with this curve, and particularly here. So this is the TE, and you can see how bang on. So the error bars are even small, so that we don't even see the error bars, right? It's an amazing, this is phenomenal agreement between different experiments from CMB, right? Even more amazing thing is actually this, right? So this underlying curve is not a best fit to all these data points. So the underlying curve is a best fit only to Planck, and Planck actually does not measure anything on small scales. So Planck gives us lambda CDM on this very large scale, but somehow you extend that to small scale, and all these experiments are just bang on that lambda CDM curve, right? So this is phenomenal agreement between all of these things, which means lambda CDM is just great, right? But however, we like I said before, we really don't understand much about lambda CDM. Okay, I said mysteries remain. There are tensions, there are deviations and extensions. There could be deviations and extensions. Okay, so that's really why we are doing these surveys. So let me show some pretty pictures. The next 4 slides. So there are multiple CMB experiments now. Okay, there are ones from Chile. So the ones from Chile are in green, and the ones from South Pole are in this brown color. Okay, so this actually has extremely good synergy with Chilean astronomy and Chilean cosmology. Okay? So because all these surveys are in Chile, so obviously the data is coming from here, and then when you go to South Pole, so Chile is also involved in this Antarctic treaty. Okay, and then these are again some pretty images. So this is South Pole telescope. Okay, again at the South Pole. So what you see on the top is actually a photo of the partial solar eclipse taken. It's like a time lapse. Okay, so then we have here we have BICEP and cake array doing this primordial beam mode measurements. So then we have Simons Observatory, and then in the future we have this experiment called Atlas, which is also going to be in Chile. Okay, so then we also had CMS4, but you might all know that it's now cancelled. Okay.
Atlas is planned for when?
2040. It's like a 50-meter diameter telescope.
Oh,
yeah. Okay, so this is what I meant by the Antarctic treaty. So Boris actually visited the South Pole telescope, right? So you can basically see the helicopters, and then the back you see the South Pole telescopes. So there is South Pole telescope, there is BICEP, there is also Ice Cube Neutrino Observatory. There are so many things at the South Pole. So this is the geographic South Pole. Okay, so South Pole telescope is so it's not a very large collaboration. It's roughly 100 scientists. If we compare that to Simons Observatory and other things, there are like 500, 600 people. And it's equally divided between students, postdocs, and faculty members. Okay, like I said before, the South Pole telescope is a 10-meter diameter telescope. I won't go into too much of the instrumentation thing because I don't really work on instrumentation. I'll just show some pictures. So here's the scale. So you can see how big the telescope is. So right now we are performing this 3rd generation survey called the SPD-3G survey. Okay, so it's a South Pole telescope 3G survey. Here's another pretty picture. Okay, so this is, so previously I showed you the solar eclipse, and this is the lunar eclipse. Okay, so this is taken by our leader rover. So it's called Aman Chalsky. It's a student at the University of Melbourne. And the other thing that you also see in the South Pole is Aurora Australis. So this is a very, very common thing that we always see. Okay. So South Pole, in fact, is the best location on Earth to do this science. It's actually even better than Chile. Okay, and the reason it's better than Chile is because when you're observing the photons in these wavelengths, the level of water vapor is a big contamination. So Chile is great because the Atacama Desert is very, very dry. Okay, but there are still, it's not as dry as the South Pole. So South Pole is full of ice, but it's dry ice. So there is no moisture in the air at the South Pole. So that's why South Pole is really the best site. But however, the logistics of the South Pole is very hard. You cannot go to the South Pole all the time of the year. You can only go there during summer. Whereas in Chile, it's accessible, 365 days per year. So having more new instruments in South Pole telescope in South Pole is very hard. Okay. So and then I want to show this data. So this is actual data. Trying to convince South Pole telescope is amazing, right? So this is also true for Simons Observatory. So what you're seeing here is an image from the Wilkinson microwave anisotropy probe. So this was launched 20 years back. So what you're seeing here is this really large blobs of dark spots and hot spots. So these are cosmic microwave background. Okay, so this is basically the fluctuations in the CMB, but it's very coarse. The resolution is like 7 degrees or something, or no, a few degrees. So you see something, but not very clear. But if you look at the same location with Planck, okay, so you might have seen this amazing image from Planck, and you can see the resolution improves, the noise in the data sets improves. Okay, so this is great. But if you look at the same location with the South Pole telescope, this is how things will look. Okay, so you see the CMB, right? But you also see these white dots and these dark dots, right? So these bright spots are actually galaxies. So these are quasars and dusty star-forming galaxies emitting in the same frequency. And then these ones are the galaxy clusters, right? So this is the inverse Compton scattering that I mentioned before, the thermal Sunyaev-Zeldovich effect. So when you have a cluster, CMB will have a decrement at that location. Okay, so so as a result, so this is in fact a galaxy at redshift 7. Okay, so these are blind detections of these galaxies, right? So for us, for cosmologists, so these are contaminations. We actually don't want these things in our maps, but this is really the signal for astronomers, right? So South Pole Telescope basically coordinates with so many astronomers who take these things and do observations with ALMA and all the other telescopes in Chile and in Hawaii. And everything. Okay. So as a result, with South Pole Telescope, the science is not just limited to inflation or cosmology, but variety of other things. Okay, so like I said, you can use KSZ, TSZ, you can do cross correlations, you can detect these high redshift galaxies and so many other things. Okay. So where is SPT observing? So this is where we are observing. So we have 3 different patches. So this red is one of our white patch, so it's very shallow. So then we have this yellow color, and then we have this green color. So together we have something like 10,000 square degrees of the sky. So it's roughly 25% of the total sky. Okay, and it has really good correlations with things like Rubin, which is this blue, and then dark energy survey, which are all from Chile. Okay, so as a result, you can do science with CMB alone, but you can also do science by cross correlating galaxy surveys with CMB. Okay. And so this is something that I wanted to show because this is a paper that we put out 2 months back. Okay, and in particular, I will just highlight the measurement of Hubble constant. Okay, so that's one of the hot parameters that we want to measure these days. So what you see on the left is the measurement of Hubble constant. So you see we get a value of 67 plus or minus 0.3, which means it's a sub-percent measurement of the Hubble constant already. So we are extremely precise. Okay, however, when we make the same measurement with things like supernova, you might have heard that the Hubble constant measurement is very, very large, right? It's something like 73. That's what supernova measurements give. So what supernova measurements are doing is that it's measuring the local universe at redshift up to 1, but CMB is measuring the high redshift universe, right? So maybe there is a systematic that we missed. There is new physics that we missed. That is happening, at the time of recombination. So basically, when we derive Hubble constant with CMB, what we do is we measure the size of the sound horizon at the time of recombination, and then we assume Lambda CDM to get Hubble constant. So Hubble constant is not one of the parameters that we actually measure; it's a derived parameter. Okay. So basically, the important point is that there are tensions that are growing, and we want to investigate this more. Okay. And so this is a paper that I'm currently writing. So what this is again, you might have heard about the recent results from DAISY collaboration. So this is baryonic acoustic oscillations. So what they said is that there is a tension between CMB and BAO, even in Lambda CDM. Okay. But if you actually look into that, look at the paper, I think there are so many systematics because most of the things come from like I think it's a systematic from low redshift supernova measurements. In fact, there was a paper that came out I think yesterday, basically like finding that out. Anyway, but this is how well we can measure. Okay, so the horizontal axis here is the dark energy equation of state, and the vertical axis is the evolution of that parameter over redshift. So then what I'm showing in the orange contour is a measurement made by DAISY. So this is real measurement. So you see, it's very deep, these 2 parameters. But when you try to do the exact same thing with supernova, from the future Rubin from LSST, you get that pink contour. So basically, they have slightly different degeneracy directions. But now, if you go from DAISY DR2 to the upcoming release of DAISY DR3, the orange contour shrinks so much. Okay, so meaning the constraints are going to improve significantly. But now, when you combine the orange on the pink contour, you get that blue contour, which is extremely precise measurement of these parameters. But now, if we add CMB to this, then we get this really nice tiny contour. So this is for SPT. So you can see that the improvement is actually roughly a factor of 6 compared to if we don't add CMB. Okay, so this is going to happen in the next 2 years. Okay, not in the next 2 decades. It's going to happen in the next 2 years. Okay, so that's why these are important things that we need to know. So next I will go into how we can probe this epoch of reionization using the kinematic Sunyaev-Zeldovich effect. Okay, which is another thing that is in its very, very primary phase. So the signal is extremely faint. So we are not in the position to measure this signal, but we are even without a measurement, we can actually already constrain this process of reionization. Okay. Okay. So what this kinematic SZ effect, I already told you that this is Doppler boosting. So when halos, which are always moving in the universe, when they move towards us, they give a Doppler blue shift to the CMB photon. Okay, so if that is a CMB photon, and if there is a halo with free electrons, and if the halo is moving towards us, the CMB photons basically get an upward shift. And if the halo is moving away from us, the CMB photon gets a decrement. Okay. And then what happens here is that, so basically that's the effect. So it depends on the number of electrons in the halo, and it also depends on the velocity of the halo. So for example, you can have a lot of electrons, but if they're not moving, there is no KZ. Similarly, there could be a lot, the halo could be moving, but if there are no free electrons, there is no KZ again. Okay. So it's basically, so this is astrophysics. This is cosmology. Okay, so KZ is sensitive to both astrophysics and cosmology. And KZ comes from 2 different sources. One is that at low redshift, so this is redshift going up to 3. We have clusters and we have halos that are moving. That gives rise to KZ. But then at high redshift, this process of reionization, when it happens, universe is becoming reionized, so there are new free electrons in the universe, and that's and these electrons are all moving. So that gives also rise to the KZ effect. Okay. Yeah, like I mentioned before. So what is this? So this is basically the period when light from the early stars and galaxies reionize the hydrogen in the universe, right? So they are emitting ultraviolet photons, and so the neutral dark universe, neutral hydrogen, the dark universe with just neutral hydrogen becomes reionized. So now we have this KZ effect. Okay. Yeah.
Questions. So what do you see kinematic and the thermal Simons-Observatory are really separable effects? Or
yes, they are separable because the Doppler boosting has no dependence on the frequency.
Okay.
Whereas the thermal Sunyaev-Zeldovich effect actually depends on the frequency.
Okay, so you mentioned different frequencies, and then
and then you differentiate between the two.
Then the other one is that the velocity is through cosmology.
Yeah.
But I guess mixed up with the local.
Right. Yes. Well,
you subtract for sure the other expansion that you have to do, no? But then
sure.
Of the redshift. Then you have.
Oh, I'm not talking about the Hubble flow, right?
It's exactly. Then okay, it's the galaxy moves also with the upper flows.
Sure. So in the linear regime, let's say everything is fine. But when you go to like extremely small scales, things become even super complicated. Yeah, there could be like other nonlinear things which we don't understand.
No, exactly.
Yeah. So we don't go to very small scales. We just cannot go to very small scales because this effect is already super hard to measure. And on extremely small scales, our data is just dominated with noise and all the other garbage things that we have.
Okay. But then we will less later.
Yeah.
Okay.
Yeah. Okay. Yeah.
I wanted to ask you if this effect is only with the velocities along the line of sight, and
that's right.
You don't.
Yeah. So when it's in the transverse direction, it's a different effect. It's called the moving lens effect. So yeah. So when it moves in the transverse direction, basically what happens is these halos are gravitational potentials, and this halo is moving in this transverse direction. So basically, there is a time derivative of the gravitational potential. So what it produces, it produces a dipole in the CMB. And the dipole is aligned with the direction of the transverse velocity. So it is another exciting probe to measure, but it has never been measured so far. Yeah. So that effect, for example, that has nothing to do with astrophysics. So if you measure that effect, we can basically study gravity with that effect. But it's just really hard to measure.
I guess there's you expect to measure it sometime in the future.
Yes.
What do you need to measure it?
Right. So an indirect measurement will be hard. So what you can actually do is you can use galaxy surveys. So basically, if you use the linear regime, you have the over densities of galaxies, and the over densities are the gradient of the over density is proportional to velocity. So once you have the transverse component of the velocity, you can assume weights based on that angle, and then cross-correlate that with the CMB, and then measure it. Yeah.
When do you expect to get it? That's realistic or
it's so I wanted to measure it 4 years back. I started working on it, and then it just turns out that when we do this, we basically measure all the other photons. So it's really hard, but maybe with Simons and Simons and Daisy, you can probably do something.
Okay.
Yeah.
Okay, so it's a reach of.
Yeah. It's not it's not 20 years from now. It might be done in the next 10 years. Okay, so now let me get in again into this reionization. Okay, so this is a simulation showing how reionization happened in the universe. So all these black regions, right? So this is just this boring neutral hydrogen. Okay, but you can see these blue regions. So these are the regions where electrons are being kicked off from the neutral hydrogen atom. And you can see over time, these bubbles are growing. Okay, so basically what happens is that over time, this reionization process is expanding, and at some point it will stop when the universe is fully reionized. Okay. So how can we detect this? Okay. So one of the key parameters in Lambda CDM is a parameter called tau. So it's called the optical depth to reionization. Okay, so this is something that Planck measures. Okay. So let me skip the first one. Let's go to the second one. Okay. So what happens here is that initially there was polarization, right, at the time of recombination, but later at the time of reionization, you have more polarization signals. Okay, because there are free electrons, and because of Thomson scattering, you have more polarization. Mostly just E mode polarization, no B mode. Okay, but at the time of reionization, the size of the universe is much bigger. So basically, what happens is that if you look at the polarization data at extremely large scales, you get a bump due to the process of reionization. Okay, so what this bump is telling us is basically telling us that the universe has reionized. That is this new polarization signal coming from. So if you measure this bump, we actually constrain the optical depth of the universe. Okay, so that's in fact what Planck does. Okay, however, this measurement is extremely hard to make from ground. So meaning we just cannot improve this measurement, right? So whatever Planck has measured, that's it. So in the future, LightBird can improve this measurement, but LightBird is it's far in the future. The experiments like CLASS in Chile can measure this, but to do this from ground, it's hard because we don't observe the full sky from the ground. So the error bar on this measurement will be super large when we do this from ground. The other problem is that we actually don't understand so many systematics on these large scales from ground. So it's just almost impossible to measure this. Okay. And the other important reason for this is that when we convert this into how the universe actually reionized. So this plot is showing the ionization fraction of the universe. 0 meaning universe is filled with neutral hydrogen at high redshift. 1 meaning universe is fully ionized. Okay. So it's above 1 because of helium reionization. So I'll not get into that. But you see, at high redshift, universe is neutral. At low redshift, universe becomes fully ionized. But now what you can do is you can do all the funny curves into this. All these different funny curves give the exact same bump in the E mode power spectrum. Okay. So even if you measure this, you won't be able to understand how that process actually happened. So that's why we want to go beyond that signal. Okay. So now what we can do is we can use this kinematic Z effect to measure this signal. Okay. So here's a simulation showing how this process of reionization actually happened in the universe. Okay. So here there are 3 different simulations. You may not be able to see like differences between the 3, but if you look very closely, on the left side you have more small scale, whereas on the right, you see like a big hot and cold spots, okay? So what you can do is you can compute the power spectrum and you get this plot, okay? But what I want to emphasize here is that the vertical axis of this plot. So this is in microkelvin squared, okay? Same thing as what we do when we do CMB power spectrum. And the scale goes from 0 to 4 in linear scales, okay? But what we actually see with the data is not just this. We actually see all these other crap, okay? Well, first is that on small scales, we mostly just see the astrophysical foreground. So these are those bright spots in the maps that I showed before. So those are basically contaminations that completely kill the cosmology from our data. So we want to be very careful about how we analyze these things. Then on large scales, we have the CMB, the primordial CMB. So as a result, KZ is here. So in the previous plot, I showed linear scale going from 0 to 4. But what we actually measure is something like this. So now it's in log scale, and the vertical axis goes to like few hundreds. Okay. So basically, what this means is that. So previously, I showed you these maps of CMB. I said the big blobs are all cosmic microwave background. But if I show a map of that, like that in the future, even in the future, you will never be able to see that KZ. It's just impossible. We will never be able to do that. Not right now, not with any future experiments. However, you can make statistical detection, so we can actually compute the power spectrum. We can compute the 2-point correlation function. We can compute the 4-point correlation function, and that is actually pretty promising. So what does this mean? If we look at a map and if we say that's KZ, that's basically like infinite signal to noise, right? If you can just look at the map and say, wow, that's kinematic Z, we will never be able to do that. Okay. So the other important point about this KZ is that this KZ effect is very, very non-Gaussian. Okay, because these are these patchy things, right? So these are patchy bubbles, and when something is patchy, it's very non-Gaussian. So when we take a map of the CMB map, when we take the CMB map and you just histogram all the pixels, you will get a nice Gaussian distribution. But if you do the same thing for KZ or anything else, you will actually see a skewness, or you will actually see signals that are non-Gaussian. And when something is non-Gaussian, we don't have to stop it at just power spectrum. So we can actually compute the tri-spectrum. Okay. So this is the paper that Kendrick Smith and Simone Ferraro put out in 2016. That's when I finished my PhD. So what they said is that instead of looking at the power spectrum, if you actually look at the KSG tri-spectrum, you can constrain reionization even well. Okay. So what they are showing here, so this is the toy model. So don't take into account, don't take this into don't have to take all the details into account. So this horizontal axis is redshift. Vertical axis is showing the derivative of the tri-spectrum. Okay. And when you see the derivative, it's bimodal. Okay. So what you can see here at high redshift, you get a higher tri-spectrum compared to the thing that you get from this low redshift kinematic Z component. Okay. So as a result, when you look at the tri-spectrum of the KZ, you're basically probing reionization. Okay. So yeah, so like I said, that was in 2016, and then no one tried this because we know that this is just super hard to measure. But then later, last year, within FPD, we were talking about this, and then said, okay, let's just try this. Okay, and then initially things looked really promising. We actually thought we were going to detect this, but later it turned out it's not a real signal. Okay, so what I want to show here is like how this estimator works. Okay, so this is how CMB lensing also works. Okay, so what you see here is a map of a Gaussian random field. So this is CMB. Okay, so this is a simulation. But what happens later is that halos form in the universe, and then they cluster among themselves, right? So over time you have like some clustering of galaxies there and some clusterings of galaxies here. Okay, and now what happens is that they interact with the CMB photon. Okay, because they are in the foreground, so they interact with the CMB photon. So when they interact with the CMB photon, basically what they do is they suppress the CMB photon because of optical depth. Okay, so that's less interesting. But another important thing here is that so you have some clustering of halos on small scales in a given location. Okay, and then you have some clustering of halos, let's say in this location. But what happens is that both these clustering in the foreground, if there is like a long wavelength gravitational wave mode, gravitational lensing mode, when it passes, it basically introduces correlation between that cluster and this cluster. Okay, So when we detect that correlation, we actually reconstruct lensing, right? Because the length of that correlation basically corresponds to the size of the structures in the universe. Okay. So similarly, if both these clusters are moving with a cosmological velocity, that also introduces correlation. So when we detect this correlation, we actually reconstruct velocity, or we can reconstruct CMB lensing. Okay. So this is the estimator that we use. So we did this, and then this is what we observed. Okay. So the other important thing that I want to mention here is that you might have seen like CMB power spectrum plots. So normally when we plot the horizontal axis, we use multipole and we use a script L, right? But if you look at CMB lensing, we don't use script L, we actually use this BL. So the difference between the two is that this is a reconstructed large scale effect. So it's not the actual thing that we measure. It's a reconstructed large scale effect. Okay, so that's why we use the BL. Okay, so we measured this. So this was accepted in PRL last year. So clearly there is a detection. So this was a 10 sigma detection of the tri-spectrum. Okay. Unfortunately, though, when we try to compute, what do we actually expect from our data, given some simulations, given some noise, given other signals, we get this thing, right? So that thing is really a good match to the data. Unfortunately, this expectation has no KZ in it. So basically, we are measuring the tri-spectrum, but it's not KZ, it's all the other garbage that we still have in our data. So we try to make sure that those things go away, but they don't, because it's really hard measurement. Okay. So now you can see if I subtract this black curve from all these data points, all these green points will be around 0, meaning it's not a detection of the KSE signal. Okay.
I'm sorry.
Yeah.
Go back to the slide.
Yeah.
So how do you know the one?
Yeah.
You said that these two regions,
yeah,
they belong to the same structure.
Well, they maybe belong to they don't belong to the same structure.
Okay.
So they are different structures. So these are small scale effects, but they both see the same large scale modulation in the foreground.
Okay. Okay.
So that modulation could be because they both see a really massive structure, and they both get lensed by the same amount.
Okay.
Or they're both moving with the same velocity.
Okay, I see now.
Yeah.
Thanks.
Okay. Right. So obviously we didn't detect this, but we still trying to see if we can do some constraints on reionization. Okay. So what we try to do are these two parameters. So the horizontal axis is basically the redshift width of this process of reionization. On the horizontal axis is the midpoint where universe is 50% reionized. So the main thing here is that this looks really bad because they both regenerate. We don't really constrain anything. Okay. However, this is not all, because astronomers have measured this high redshift universe, right? And what they've done is they made plots like this. So they have measured these high redshift galaxies. So like, for example, from JWST, from Hubble Space Telescope, and they try to infer the amount of ionization in the universe. So you see at very high redshift, this is close to being neutral, but at low redshift, things are fully ionized. Okay. So that effect is called the Gunn-Peterson trough. So it's a very, very famous effect that was measured around 2006, I think. Okay. So basically what that is saying is that around redshift 5 or 6, universe is fully ionized. And we can use this piece of information. So this is a completely independent information from CMB. And when we use that information, we now make an exclusion. Okay. So what this does is that it basically removes all this region, and now we end up in this location. Okay. So basically what we obtained is delta Z. So basically the width was less than 4.5 with 2 sigma. So what this means is that from Planck, you can measure what was the midpoint of reionization. So let's say if it's around 7 or 8, this is saying that reionization should not have started at redshift 20, because if the midpoint is 7, the maximum width that it can go up to, it will be like 7 plus 4.5, right, in 2 sigma limit, right? So what it's doing is it's already ruling out very, very slow and early reionization models, right? So because people have worked on, galaxies at redshift 40 already starting to reionize the universe and things like that. So those things are already ruled out with this non-detection. Okay. But in the future, this is actually better. So if we do the same thing with Simons or with SPD, so the green band basically shrinks to this brown band. And most importantly, you can see high redshift piece, it is extremely highly constraining, right? So it basically says that around redshift 15 or something, you should be fully neutral. Okay, so it's going to be really nice, okay, in the future. Okay, so I think I'm going to skip the TSE. I will just quickly show you, like with very few slides, maybe like 4 more slides of what we can do with cross correlations. Okay, given that we are in Chile and there are so many surveys. So I want to show this plot to tell you why these cross correlations are important. So what this plot is showing is that on the horizontal scale, the horizontal axis, you see the scale of the perturbations. So this is basically the Fourier wave number. So when you're looking at the left side, you're looking at large scales, and on the right side, you're looking at small scales. Horizontal axis is redshift. So when we use primary CMB, we are measuring the high redshift universe on very large scales. When we use CMB lensing, we again measure large scales, but we measure some mid redshift universe, because that's where lensing is happening. Because lensing is happening because of structures, and structures form around redshift 5 or 4 or 3 and so on, right? Structures didn't form at redshift 50. Okay. But when people, when we have results from dark energy survey or in the future by Rubin, when they talk about weak lensing, they are measuring small scales, but at low redshift, right? Because Rubin does not observe things at redshift 2. It mostly only observes things up to redshift 1 or 1.5. Okay, but when we do a cross, we're actually probing somewhere in the middle. So what this means is that when we measure that, when we measure this, and we measure this, jointly, we can actually constrain so many things. Because there could be some systematics here, which we don't know if we just do this measurement. There could be some systematic there, which we don't know if we just do that measurement. But the fact that if we do all the things, we can actually constrain both cosmology and the systematics really well. So that's why these things are important. And this is basically a plot showing how well we can measure this cross correlation. So on the left side, I'm showing what you get if you cross correlated the CMB lensing map from SPD with the lensing map from Euclid. Okay, so you can see that these are 3 redshift bins, and you see these error bars are so small, meaning these cross correlations are going to be measured at extremely high significance. Okay, and on the right side, it's a different observable. So let me not do that. Okay, so this is my last thing. So all these things that I've been talking about are basically from halos, right? So I talked about halos moving, having electrons, producing KZ, TSE effect, and lensing. But universe does not have only overdense regions. Universe also has underdense regions, right? So if you look at, for example, a map of dark matter, you'll see nodes where there is basically more clustering of matter, but there will be locations where there is less clustering. There's basically like very, very less number of halos. That's also cosmology. And so I wanted to see if we can actually do something with those underdense regions, right? So what we did is to cross-correlate cosmic voids with the CMB observables. In particular, we tried to do this with CMB lensing and this thermal Sunyaev-Zeldovich effect. So these voids are coming from the survey like Sloan Digital Sky Survey, which is basically measuring spectroscopic redshift of many galaxies. Okay, it's a very old survey, and it's in the northern hemisphere, unfortunately. So we can only do this with Planck, because all the other surveys does not have correlation. Well, particularly SPD does not have any correlation with the Sloan. So what you see here is a simulation showing what we will get if you do the cross correlation. So cross correlation in the real space is stacking, right? So you basically take the location of each halo and you just stack them. So that is stacking in real space. In the Fourier space, it's basically the cross correlation power spectrum, right? It's the same thing. So what you see there is that these voids are not all the same. So in the second panel, you see a region where there is a really large underdensity. But in this panel, you see a donut-like structure, right? So there is an overdensity and then there is something in the middle. So that's with CMB lensing. So when you look at CMB lensing, you're probing dark matter, okay? Because it's just mostly dominated by dark matter. But when we use thermal SE, you see that they both look very similar, but thermal SE is actually probing hot baryons, right? So these are electrons, which give rise to this thermal Sunyaev-Zeldovich effect. And as a result, when you detect this, you are basically measuring hot baryons in these underdense regions. The fact that they both look similar means if you take these two measurements, you actually can say about how baryons trace dark matter in these locations, right? So that is simulation, and this is data. So on the left panel, I'm showing the actual measurement that we did with Planck lensing and voids from Sloan survey, and you see that the measurements this year, and then the expectation from SIMS are there, and you see that this is roughly like a 6 sigma measurement of the total sigma. Then we tried the same thing with the thermal SE, and you see a very similar pattern between these two. Right, so this is still in our works, but what this means is that when we detect this and when we take these two things into account, we can actually try to understand the relation between dark matter and hot baryons in these locations. So this is something that we are doing right now. Okay, with that I'll summarize. Yeah, the main thing is that the SPD and Simons and all the future surveys are amazing for cosmology and also astrophysics. Okay, I mainly spoke about kinematic SZ and reionization, which looks pretty promising in the future. I didn't talk about thermal SZ, but I think it's okay. But then I also showed some results for this, tracing dark matter and baryons in cosmic quads. So, things look pretty promising for the future, and we have all the data. We just have to do the work. Yeah, thank you for listening.
Okay, question. Sorry.
Yeah.
Listen, really not involved, really.
Okay.
About this one,
Yeah.
I didn't understand why voids, cross-correlating simply with voids gives information about the proportion, let's say, between dark matter and baryons.
That's right.
Why? I mean, okay.
But not with lensing alone, only when we combine the two.
No, exactly, yes.
Yeah.
But why? I mean, you have voids that are the darkest spots, let's say,
Yeah.
Because you said, okay, those blue stuff are this is simulations for
Right.
So the blue stuff are voids.
Well, this is also a different kind of void. It just seems like it's it's very complicated. So these underdense regions are not all the same.
Sure. I mean,
right. It looks like they have funny features.
Then why do we do the ratio between dark matter and baryons?
Oh, because with that measurement, you only measure dark matter, right? When you're just looking at lensing, you're probing the total matter content.
Yes. Yes, it's true. Yes.
Right. But when we are probing thermal SZ, you're only probing baryons. Yeah. And the fact that they look similar means that there is some correlation between the two.
Okay, so the void for the last one, thermal and voids. So why have to cross-correlate then?
Oh, because if we don't do this, we won't understand. We will only know that there is some total matter in that location, right? So we know that so there is dark matter in there, sure. But we also want to understand, how baryons are distributed in the universe, right? So there are things like missing baryons, all of those kinds of issues, right? So that is challenging cosmology. So if we do these kinds of measurements by cross-correlating lensing with these other baryon probes, we basically know if there is really missing baryons or if we are actually missing something else.
Okay.
Yeah.
Okay.
Yeah.
And on these same plots, the simulations, I maybe expect that TSE, like the map for the voids, are smaller. Is that the case, or they're kind of the same size with the one?
They are the same size, so they're on the same scale. Yeah, it's because these are extremely large regions. Well, and the other thing is that Planck has extremely poor resolution, so you won't be able to probe very small scales of Planck, unfortunately. But with Simons, we can do this better. Yeah.
Any other question?
Yeah.
You're going straight to the 4 points.
Yeah.
Why not the 3 points?
Thank you. Yeah. So 3 point for KZ is 0.
Yeah.
And the reason is because some halos, like I told you, some halos are Doppler blue shifted, so they get an increment. Some halos are red shifted, so they get decrement. And in the universe, there are equal number of halos moving towards us to away from us. So when you just stack them, you get 0.
Yeah.
So as a result, all the odd points vanish.
Okay.
That's why you go to dry spectrum from power spectrum. Yeah.
Is it worth going for higher endpoint?
Yeah, we can also do. So people have tried to do, like this KNN distributions, where basically try to, for example, you can do like a Bayesian method, where you don't measure any of these individual things, but you basically measure all the things. Just turns out it's still really hard. Well, the other thing is also, so when we do that dry spectrum, right, we are basically like squaring the map at some point. And since you're squaring the map, you're also squaring the noise, and that also goes up. And when you go to like even higher order functions, the signal noise is even smaller. So it doesn't seem to add a lot. But yeah, something to think about in the future. Yeah. But it seems like even without the detection, we can already do something, which is something that and this is completely independent of Planck. Right? So yeah. So for example, in the last couple of months, there has been so many papers, trying to, because when DAISY, they came up with this tension between CMB and DAISY, people have proposed that, and also I don't know if you've heard about this thing where CMB lensing prefers a negative neutrino mass, right? So this is another thing, that we, but of course that does not mean anything physical, like neutrinos as cannot be negative, but it turns out that you can actually increase the optical depth because they are fully degenerate. So when you increase the optical depth, you can basically get rid of that tension. So you get rid of negative neutrino mass tension, you get rid of CMB DO tension, but optical depth has to be 0.09, which has already been ruled out by Planck. Right. So you can get some crazy result for optical depth, but that will fix all the other problems. But what KSE is saying is that such high optical depths are not possible. Right. So it's all kind of connected.
So what's the way out of that?
So the way out is probably there's a systematic. So actually, one thing that I wanted to show.
You showed the plot before, respect to lab.
Yeah, but that was a forecast, so that does not really have the actual contour. But I wanted to show this one. If you look at this like really closely, so this is a plot from DAISY paper. I really think it's okay. It's very crowded plot. Let me just tell you like maybe 2 plots. So on the top panel, so you're basically they're plotting. So this is from DAISY. They're plotting the observable for this BO, okay, as a function of redshift. So you see all the data points, okay, and then you have these different curves giving different predictions for lambda CDM. Okay, so the Planck lambda CDM is here, and then this year 5 supernovae only lambda CDM is there, and so on. Okay, so all those data points are pretty much consistent with most of those all the curves. So that doesn't prefer any crazy cosmology. Okay, but if you look at the bottom panel, they plot supernovae measurements, right? So they plot the expectation for supernovae distance modulus measurement, because that's what you're measuring when you're measuring supernova. You're measuring the distance to a particular redshift. So just exclude this point, take all these other points. All these points are basically consistent with lambda CDM, right? So this, and maybe this is slightly off, but these are all consistent with lambda CDM. Yeah, that one. But it's basically that this redshift, this low redshift point, it basically pulls everything to that thing.
No, when the other one is
right. So this one is off, right?
No.
This one.
No.
Here.
The rightist.
Right.
No.
Right. So none of this match this lambda CDM, right? Because this lambda CDM is kind of like that. But if you take the CMB lambda CDM, things are all fine.
Okay.
So this is CMB lambda CDM is basically the same thing happens here. It's basically this low redshift point that's pulling things. And the difference between these two are, so that's the supernovae from dark energy survey, this supernovae from this Union 3 sample. But if you actually take the supernovae from this Pantheon sample, you see things are very different. Okay. So I think it's just some some really bad combination of data. And people have written. I think a Daisy release came a few months back, and I think few people have written about these things, and also like higher tau and all those things.
It's also the combination of the Daisy data, no?
Yeah.
Are provided. For instance, in the DR1, but there's data,
Right.
which is ETH over RT,
Right.
M over RT.
Right.
And for instance, okay, the paper, we show that okay, there are two bigger points that
Right.
are outliers, no? It's
Right.
interesting. So, but then if you use DR2 data,
Yeah.
and they're provided with a different combination of data,
Right.
which is DM over DB,
Exactly.
all that stuff, no?
Yeah.
Now, actually, okay, there are no, I mean, outliers are still there.
Yeah.
But they are not statistically consistent. I mean,
Not statistically discrepant.
exactly.
Exactly.
And so I was guessing maybe there's also a problem of how they do the fixed length vision of cosmology.
So yeah, so they basically say that the systematics and Daisy analysis is actually like just zero. Because I think their claim is that there could be systematics in individual measurements, but what they're measuring is basically the clustering of all of these galaxies, and they see that bump around this 145 megaparsec. It seems like none of those systematics can actually shift that bump. It can shift the amplitude of the bump, but not actually the location of the bump. And yeah, Daisy measures the product of Hubble constant and the sound horizon. Seems like none of those things are sensitive to any of those systematics, but who knows? Yeah. Yeah, but I think exciting times ahead. All these new data.
By the way, are there questions?
On Zoom? I don't see any. Are there any questions on Zoom? I don't see any questions.
No, thanks.
Okay. Yeah.
Okay. If there's no more questions,
Oh.
okay. You show a plot with different color lines. And you said you couldn't define the mechanism of reionization.
Yeah.
You can explain them?
You mean this one?
No.
Oh. You mean this one?
Before.
Before. Oh, you mean this one? No. Okay. Oh, this
when it showed like the transition between the fully right, the ionized, and the before, I think. Yeah.
what's before?
That one.
Oh, year. Yeah. Okay. Yeah. Good. Yeah. Right. So yeah. Right. So the reason that it doesn't really prove the process is because what Planck is measuring. Because in CMB we are always measuring the integrated quantity. So we are basically measuring the total integrated optical depth, and we are not sensitive to what's actually happening at different redshifts. So basically, all this is saying is that the total optical depth, due to the extra polarization that happens during reionization, is just produces a bump. And apparently, it's just not sensitive to the process itself.
And the different lines, what are they?
Oh, those are just like different reionization models.
Okay.
I think there are some funny models there. One of those models is this thing, like this sine curve, right? So apparently it's not actually as, when I first saw this, I started working on reionization only like 2 years back. And I thought, wow, how will someone even put a plot like that? But apparently when first WMAP measured the value of optical depth, they measured it to something like 0.17. And at that time, that model was one of the hottest topic in this field. So basically what that is saying is that universe is starting to ionize, right? And then something happens in the universe, that ionization stops. And when ionization stops, universe is expanding, but it's nothing is happening. And so the ionization fraction is dropping again. But then later, due to some large amount of galaxies or quasars forming, universe becomes so rapidly ionized again. Right? But it turned out that measurement from WMAP is actually a systematic. Yeah. Yeah. So So I think that's so those actually have some physical motivations, but I don't think anyone actually seriously considers those kinds of models anymore. Yeah, I think it's called like the double reionization something. Yeah, but yeah, good. Thanks.
So what's the most reasonable model right now?
So the reasonable model is basically, you know, right. So that's the reasonable model, but the error bars are all super large, right? So you want to connect all these things. So
It's a model or is it?
no, these are all data points,
Yeah.
right? So again, because the error bars are so large, many models will still fit all these things, right? I mean, honestly, I'm also not very sure about how much to trust these measurements. So for example, when I made this plot last year, so this point, and this point, so this is the highest redshift, right? Between the time when this paper was first put on the archive, and then 6 months later, they had 3 versions in the archive. This point has basically moved up or down, like even above the error bar. So I'm not sure how much to trust these things, because it's a very hard measurement to make. So I think what they're doing is they are measuring the spectra, and when they measure the spectra, there is this huge absorption in the spectra, but they have a really small region to predict how much of the absorption actually happening. And it's much easier to do at low redshift because you have a huge region to measure. But at high redshift, you have a very small region as a function of wavelength. I think that's why it's hard. But yeah, so yeah, I'm not really sure about how much to trust that particular data point. Yeah.
Well, thank you, Srini,
Thank you
for your talk, and thanks you all of you for coming. So I think Srini deserves some.
Thank you. Yeah.
Something that philosophy is like you of